Alright, so in this video I'm going to go over Lab 6, Impulse and Momentum. And this is going to require this Mechanics Lab software again. So we'll just go in here and get this started. And let me just open this again. Right, so in particular this is going to be the momentum experiment. And essentially what we're doing is just colliding objects together to kind of see how conservation of momentum works. So we pick momentum. And you can kind of think of these as two hockey pucks on an air hockey table. Essentially there's no friction between this and whatever they're sitting on. And you have this little cursor that you can move around to measure distances between things, and we're going to need that. So just like last time, if you can put this somewhere and then right click, and this will bring up this little spinning box, and that marks your first position. And if I move it somewhere else and right click again, that gives me 2 points, and then this tells me how far apart they are in centimeters. And if I right click again, it gets rid of it. So we'll need that later. You can adjust the mass of these two objects here. We'll be changing those throughout. And you can change the initial velocity of this guy by pulling, clicking on and pulling this black dot around. So for example, if I pull this to the left, minus 27.9, and I hit launch, this thing will fly off to the left with a speed of 27.9 centimeters per second. And each of these dots here, I believe, represents a tenth of a second. Let's see, just to make sure. Yeah, each dot is generated a tenth of a second apart. Okay, so if I measure the distance between this dot and, let's say, this dot, that would be 1, 2, 3 dots away. So that's 3/10ths of a second, and the distance is 8.36 centimeters. So from there I can calculate the velocity by doing this, which is delta x, over the amount of time, which is 3/10ths of a second. So we'll get into more of that when we actually do these experiments. So I'm just going to reset this for now. So I think there's 3, maybe 4 different things that we want to test here. This all has to do with conservation of momentum. So the first one is going to involve just adjusting, in fact I think all of them are just adjusting the velocity, initial velocity of this puck, and changing the masses. So for this first part, let's just copy what's here, and then we'll fill in the data. So V set, sigma V set, delta x, sigma delta x, delta t, v, and sigma v. Right, we'll just make this a little nicer here. Right. So the first thing it wants us to do is to set the velocity between minus 15 and minus 25 centimeters per second. And this part is just to sort of calibrate our measurements here and figure out if what we're doing aligns with what the program is telling us. So I want to pick this and put it somewhere between minus 15 and minus 25. So I'm just going to randomly pick minus 20.5. So that's going to be my V be set here. And I'm going to assume that my uncertainty is just 0.1. So a tenth in whatever the last digit is. That's what I'm going to assume that is. And if I let this go, that's going to go off, hopefully at 20.5 in that direction. And so in order to test this, I'm going to pick a certain number of dots, say like this, 1, 2, 3, 4, 5, 6. So that's going to be a delta t of 0.6, right? 6 out of 10. And my delta x is 12.36. Okay, and actually it should be negative because I'm going from right to left, and this is a vector, so it should be a minus sign. And the delta that I'm going to get, the sigma, is again just going to be a tenth, or I think they suggest a certain amount. Yeah, so they say it should be about 0.05 centimeters, and it should be square root of 2 times that. Since you're taking two measurements, you have to add the uncertainty and quadrature. So this is going to be square root of 2 times 0.05. That's going to be my uncertainty there. And since I have a delta x and a delta t, my v is just going to be this divided by that, minus 20.6, and yeah, that looks pretty good. Exactly what I would expect. The sigma v, you want to calculate that with quadrature. See if they give us the formula somewhere. Yeah, right. So because only delta x has uncertainty, we don't have to worry about delta t or adding in quadrature. So it's just going to be v times, actually it should be the absolute value of this. So it's going to be v times sigma delta x divided by delta x. And that's my uncertainty in the velocity. And so you can see this value plus or minus this captures this value. So everything works out nicely. So that was just a test to kind of calibrate the system. Now we're actually going to collide the pucks together. And let's see. When we do that, we have to write down what our masses are going to be. And so essentially we want to copy what's in here, but with some additional information. So we have the masses of each, and I guess there's no uncertainty associated to those. But then we have various velocities. So v1 initial, the initial velocity of the first puck, sigma v1 initial, and then we have v1 final, sigma v1 final. And what we're going to do here is set the second mass to be very large, about 10,000 kilograms. And so what will happen is when we bounce this, when we shoot this towards this, it's just going to bounce back with this approximately the same velocity, because this is essentially like something that's immovable, right? It's not going to, 10 kilograms hitting 10,000 kilograms is not going to do anything. It's just going to bounce off. So we assume that the final velocity of this guy is 0. Now again, we want to set the initial velocity somewhere between 15 and 25. So I'm just going to make it, I don't know, 18.3. And my uncertainty again is 0.1. And the masses are 10 and 10,000. And then, so actually I want to put delta x here because I'm going to have to figure out what that is. And a delta t. Then I can put my V1 final and my sigma V1 final. Okay. Sigma delta x is going to always be the same. Square root of 2 times 0.05. It's going to be the same for everything. So I expect that this is going to bounce off with the same velocity going in the opposite direction. So let's see what happens. And that's basically what it looks like, because these dots here comprise part of the motion when it's going to the right, and then also the motion when it's going to the left, and you can see you can't really tell the difference. And that's because the speed didn't change, and so the dots, the spacing between the dots looks the same. So if I pick a, some set of dots over here, go from here to here, let's say it's 1, 2, 3, 4, 5, 6, 7. So my delta t is 0.7. My delta x is 12.71. And so, and of course that has to be negative. Let's not forget that, because again it's going to the left. So this is delta x over delta t. And you can see we get pretty close to the value I started with. Of course, it's not exact, and that's because the momentum isn't exactly conserved. Right? There is a tiny bit of momentum given to this guy, but it's very small. That's because it's really not fixed. Right? It does absorb a little bit of energy. This is again just the absolute value of this times sigma delta x divided by delta x. Oops. Okay. There. So that's well within the uncertainty. And then it wants us to calculate the total change in momentum. So this is delta p total. And then the uncertainty in that. And then the impulse. So J here is the impulse. And so let's see. Delta P total is delta P1 plus delta P2, which is just delta P1. And so in this case, it's nothing more than mass times the change in velocity. Okay? So this is just going to be equal to mass times V final minus V initial. All right, that's delta P. Invalid. Oh, forgot the times. There we go. So that should be my delta P. And the uncertainty is given by this quadrature here. So this is going to be mass times the square root sigma V1 plus sigma V final. There we go. And then finally the impulse is from equation 2, which is what I just calculated. So let's see. Okay. Yeah, I'm not exactly sure what you're supposed to do with that. So I guess just forget it. Because the equation is just the same equation for this. So forget that part. It doesn't matter. Um, okay, so that's pretty much it. And we got the result we expected. So now we're going to basically do another experiment, but we're going to keep the masses equal. And so this is going to require us to calculate more things. Let's see, what do we need? We're going to need the mass of each. We're going to need the initial velocity of the first puck. We're going to need the final velocity of the first puck. And these are actually expected. So this is going to be, let's see, V1 final expected, sigma V1 final expected, V2 final expected, and then the measured values. And in this case, in order to get the measured values, we have to compute the delta x's, V1 final measured, V sigma, there. So lots of stuff to calculate here. Okay, so in this case, these guys are going to start with the same mass, and what's going to happen is this puck is going to hit this one and transfer all of its momentum to it. So this one is going to stop, and then this one is going to move at the same speed that this one originally had. And again, we want to pick something between 15 and 25. So I'm just going to pick 22.5, 0.1 uncertainty. And if we look here, what I expect is for the elastic collision, the final velocity of the first puck should be given by this equation. And so if we plug this in, of course we're going to get 0 because the masses are the same, but I'll just plug it in anyway. It's going to be that times the initial velocity divided by the sum of the masses. Okay, so that's what we expect to get. And the uncertainty, well, that depends on the uncertainty and the velocity. So this is just going to be that times sigma divided by that. And of course we get 0 because this is 0. And the expected velocity for the second puck right. let's see, well, in any case we can write the uncertainty here is going to be m1 over m2 times the square root of the initial one squared plus v1 final, sigma v1 final expected squared. Boom. So that's our sigma there. And this should really be equal to just using conservation momentum here. V2 final is just going to be equal to m1 times v1 initial minus v1 final divided by m2. And you can see that they're exactly the same, which, you know, kind of guessed from common sense. So let's see what happens when we run this now. And there we go. We get exactly what we thought we would get. I can't measure any final velocity of the first puck because, well, there isn't any. So this is just going to be 0. But for the second one, I can pick this dot, maybe this one. 1, 2, 3, 4, 5, 6, 7. So D2 is going to be 0.7, and the delta X is 15.47. And again, this is that square root of 2 times 0.05. Okay. And so V1 measured is just going to be 0 because it didn't go anywhere. So that divided by delta T1 actually gives you a problem because division by 0. So that this just ends up being 0. That means that's going to be 0 as well. But this is going to be delta x2 divided by delta t2, 22.1, so it's close. You know, I'm not exactly all that precise with measuring here. That's why we have uncertainties. And so this again is going to be that times sigma delta x2 divided by delta x, which is that. And well, unfortunately, it doesn't agree within the uncertainty, but I guess that's okay. Not too big of a deal. So that's that. And finally, let's see, when we do the last part here, we want to basically do the same thing. We're going to set the yellow one to 20 and leave the blue one at 10. So leave the blue one at 10, set this one at 20. And again, we want to send the yellow one, or the blue one, to the right at some velocity between 15 and 25. I guess I'll just pick 18.3. And we can copy all this because we're going to compute the same type of stuff. That's going to get changed to 20. This is going to get changed to 18.3. And what we're going to find, what we should find, is that this puck will bounce off, but it will bounce off with a slower speed than what it started with. And this one will actually go to the right, because now it's not huge, it's only 20. So let's see what happens. Yep, that's exactly what we thought would happen. So this one bounced back with a little bit of velocity still left, and then it gave some to the other one. And so now, essentially what we want to do is try to predict what our velocity is going to be. We did that here. And so we expected that the final would be 6.1, and the final V2 velocity would also be 6.1, which is interesting. It just so happens picking 18.3 gave us exactly the same final velocities here. It's just a coincidence, really. And so in order to confirm that, I have to measure. So let me just pick a random dot here, and then another one that's not too far away. So 1, 2, 3, 4. And so my delta T1 is going to be 0.4. My delta X is 2.23. And then if I come over here, one, 2, 3, 4, 5. So this is going to be 0.5 and 6.49. And let's see, this is going to be delta x1 divided by delta t1, which is close, 5.575. It's close. This is this times, oops, that divided by that. There's my uncertainty. And then this one is going to be that. So why did this come out incorrectly? Let's see. Or not that one. Why did this one come out incorrect? Alright, so it's mass 1 times initial minus final divided by the mass of 2. Oh, that's because the final should be negative for this velocity. Why is it not negative? Oh, because I subtracted that one from that one. That's why. There we go. Now it's correct. So if I just put a minus sign here on the delta x, because it's going to the left as it should be, then I get that my measured final velocity for the first one is close, and my measured final velocity for the second one is also close. So that situation worked out okay. So that's it for this. So hope that helped clear up some conceptual difficulties with this experiment.